Dear students, do you want to get into the fascinating world of physics? Please see this video and also subscribe to this channel.
Dear students, in this video we are going to study about various theories of light: corpuscular theory, wave theory, electromagnetic wave theory, and quantum theory.
Not because the light fails to. Unit 7 Wave optics. An age is called dark, not because the light fails to shine, but because people refuse to see. James Albert Mission. Learning. In this unit, the students are exposed to the wave aspect of light, the proof for law of reflection and refraction, the phenomena like interference, diffraction and polarization, the terms like magnification and resolving power, etc., the different optical instruments like microscope, telescope, etc. Theories on light. 7.1 Light is a form of energy that is transferred from one place to another. A glance at the evolution of various theories of light put forth by scientists will give not only an overview of the nature of light but also its propagation and some phenomenon demonstrated by it. 7.1.1 Theory. Sir Isaac Newton, 1672, gave the corpuscular theory of light, which was also suggested earlier by Descartes, 1637, to explain the laws of reflection and refraction. According this theory, light is emitted as tiny, massless, negligibly small mass, and perfectly elastic particles called corpuscles. As the corpuscles are very small, the source of light does not suffer appreciable loss of mass even if it emits light for a long time. On account of high speed, they are unaffected by the force of gravity and their path is a straight line in a medium of uniform refractive index. The energy of light is the kinetic energy of these corpuscles. When these corpuscles impinge on the retina of the eye, the vision is produced. The different sizes of the corpuscles give different colors to light. When the corpuscles approach a surface between two media, they are either repelled or attracted. The reflection of light is due to the repulsion of the corpuscles by the medium, and refraction of light is due to the attraction of the corpuscles by the medium. This theory could not explain the reason why the speed of light is lesser in denser medium than in rarer medium, and also the phenomena like interference, diffraction and polarization. 50. 7.1.2 Theory. Christian Huygens, 1678, proposed the wave theory to explain the propagation of light through a medium. According to him, light is a disturbance from a source travels that as longitudinal mechanical waves through the ether medium, that was presumed to pervade all space. As mechanical wave requires a medium for its propagation, the wave theory could successfully explain phenomena of reflection, refraction, interference and diffraction of light. Later, the existence of ether in all space was proved to be wrong. Hence, this theory could not explain the propagation of light through vacuum. The phenomenon of polarization could not be explained by this theory, as it is the property of only transverse waves. Electromagnetic wave theory. 7.1.3 Maxwell, 1864, proved that light is an electromagnetic wave which is transverse in nature. Electromagnetic wave theory. 7.1.3 Maxwell, 1864. Maxwell, 1864, proved that light is an electromagnetic wave which is transverse in nature, carrying electromagnetic energy. He could also show that no medium is necessary for the propagation of electromagnetic waves. All the phenomenon of light could be successfully explained by this theory. Nevertheless, the interaction phenomenon of light with matter like photoelectric effect and Compton effect could not be explained by this theory. 7.1.4 Theory. Albert Einstein, 1905, endorsing the views of Max Planck, 1900, was able to explain photoelectric effect, discussed in Unit 8, in which light interacts with matter as photons to eject the electrons. A photon is a discrete packet of energy. Each photon has energy E of 54 unit 7 wave optics E equals HV, 7.1. Where h is Planck's constant equals 6.625 10 to 34 Js, and v is frequency of electromagnetic wave. H. As light has both wave as well as particle nature, it is said to have dual nature. It is concluded that light propagates as a wave and interacts with matter as a particle.
Welcome to This Explainer. You know, have you ever actually stopped to think about the light hitting your eyes right at this very second? It's kind of funny. It's something we completely take for granted. But the screens you're watching this on, those highly advanced cameras sitting in your pockets, and literally the internet cables running deep beneath the oceans, they all rely on the exact evolution of scientific understanding we're going to uncover today. So let's just dive right into this and, well, shed some light on light itself. The author James Albert Michener once wrote, "An age is called dark, not because the light fails to shine, but because people refuse to see." I love that. It perfectly sets this dramatic, kind of philosophical stage for us. Because what we're about to walk through today is essentially a chronological detective story. It's the story of brilliant people who absolutely refused to stay in the dark and methodically unraveled the universe's greatest, most elusive mystery. What actually is a beam of light? All right, here's our roadmap for today. We'll cover 1. Newton's particle proposition, 2. Huygens wave counter theory, 3. Maxwell's electromagnetic breakthrough, 4. Einstein's quantum solution, and 5. The dual nature of light. Looking at this timeline from 1672 all the way up to 1905, I actually want you to think of this narrative kind of like a software development cycle, right? Every great theory acted as a patch for a specific bug left behind by the previous generation. One scientist would solve a massive problem, but then inadvertently highlight a totally new flaw, essentially passing the baton to the next genius on the list. Okay, starting off with section 1, Newton's particle proposition. So, building on earlier suggestions by Descartes in 1637, Sir Isaac Newton basically visualized a light as being made up of tiny, invisible bullets. He called them corpuscles. These were thought to be incredibly small, perfectly elastic particles with negligibly small mass, emitted directly by a light source. And because they were so ridiculously small, Newton argued that a source could emit light for a long time without losing any appreciable mass. He theorized that these particles traveled at unbelievably high speeds in straight lines through a uniform medium, completely unaffected by gravity. He even suggested that different sizes of these corpuscles were exactly what produced the different colors of light we see. And when these invisible bullets finally hit your retina, boom, vision is produced. Now, Newton's theory was great for certain things. It explained reflection and refraction beautifully. He figured reflection was simply these corpuscles bouncing off or being repelled by a medium, and refraction was them being attracted by it. But here's the fatal flaw. His theory totally failed to explain why light actually travels slower in a denser medium rather than a rarer one. Plus, it completely fell apart when scientists tried to explain more complex things they were actively observing, like interference, diffraction, and polarization. So Newton had a huge piece of the puzzle for sure, but the picture was definitely incomplete. Which brings us to number 2, Huygens wave counter theory. Enter Christian Huygens. He's the detective who proposed a radically different counter theory to go in and fix the bugs in Newton's model. Huygens imagined light not as particles shooting out like tiny bullets, but rather as a disturbance traveling as longitudinal mechanical waves. But wait, here was a catch. Mechanical waves, like sound for example, require a physical medium to travel through. They just can't travel through empty space. So to make his math actually work, Huygens had to rely on this highly convenient scientific band-aid he called the ether. This was his presumed totally invisible medium that supposedly pervaded all of space, basically giving his mechanical light waves something to ripple through. And you know what? Huygens' wave theory successfully explained reflection, refraction, and, crucially, it also perfectly explained the interference and diffraction of light that had completely stumped Newton. It was a massive breakthrough, but get ready for the next cliffhanger. Later on, the existence of this invisible ether in all of space was completely disproved. And, well, if there is no ether, and light is a mechanical wave, How on earth does light travel through the dead, empty vacuum of space from the sun to the Earth? It couldn't. Oh, and also, because Huygens thought light was a longitudinal wave, his theory couldn't explain polarization, which is a property exclusive to transverse waves. Moving on to Section 3, Maxwell's electromagnetic breakthrough. To solve this huge vacuum problem, Maxwell took a massive leap forward. He mathematically proved that light didn't need Huygens' imaginary ether at all. Actually, scratch that need for a physical medium entirely. Maxwell showed that light is a transverse electromagnetic wave. And crucially, he proved that absolutely no physical medium is necessary for the propagation of electromagnetic waves. They can travel perfectly well through a pure vacuum, just carrying electromagnetic energy all on their own. So Maxwell seemed to have it completely figured out. He solved the vacuum travel problem, and by proving light was a transverse wave, he easily explained polarization alongside all the other wave phenomena. Honestly, the scientific community thought the debate was finally over. The case was closed. Yet, the universe threw another major curveball as we entered the 20th century. Maxwell's beautiful wave theory drastically failed to explain new observations of how light interacts with matter. Specifically, it couldn't explain the Compton effect, which is how light scatters off electrons, or the photoelectric effect. That's the phenomenon where light shining on a material actually ejects electrons right out of it. A pure continuous wave simply couldn't account for how that specific amount of energy was being transferred to the electrons. And that brings us to Section 4. Einstein's quantum solution. Albert Einstein stepped up to solve this whole photoelectric mystery. And to do this, he actually endorsed the earlier 1900 views of Max Planck. Einstein realized that to explain how light ejects electrons, he had to circle all the way back to an idea that sounded suspiciously like Newton's old corpuscles. Crazy, right? Einstein explained that when light interacts with matter, it actually does so as a particle, specifically a photon. A photon is a strictly discrete, distinct packet of electromagnetic energy, rather than a continuous, unbroken wave. This realization leads directly to one of the absolutely most monumental equations in all of physics. E equals hv. Energy equals Planck's constant times the frequency of the electromagnetic wave. Now, this simple little string of characters is incredible because it permanently fuses the concepts of waves and particles together. You have E, the discrete energy of the particle-like photon, and it's directly determined by V, the frequency of the continuous wave. Which leads us to our final section, number 5, the dual nature of light. So it turns out this entire 200-year scientific debate wasn't a boxing match where wave had to knock out particle or vice versa. The universe actually required both. To sort of anchor the abstract math here, think of wave optics like a pond of still water. If you drop a stone into that still water, it creates these spreading circular ripples. Now, the water molecules themselves are just oscillating up and down, but the ripple, the wave itself, moves outward. All the points on that circular ripple are in the exact same phase of vibration, forming what we call a wavefront. Yet, even though light propagates outwardly as a wavefront like that, its actual direction of travel is still wonderfully represented as a simple straight line, or a ray. So, what is the ultimate takeaway from all of this? Well, light has a dual nature. It propagates through the vacuum of space as a transverse electromagnetic wave, proving Huygens and Maxwell largely right. But the very moment it actually interacts with matter, like hitting your camera sensor or the retina in your eye, it interacts as a particle, a discrete photon, proving Newton and Einstein right. Both theories are absolutely necessary to describe reality. I really want to leave you with this final provocative thought. For centuries, brilliant minds tried to force light into a neat, intuitive little box. It must be a particle, or it must be a wave. But reality was far stranger, and honestly, far more beautiful than our everyday categories allowed. If the very light we use to see the universe completely defies our simple common sense, what other non-intuitive, bizarre mysteries are hiding right now in the fundamental fabric of our reality? Keep wondering, keep questioning, and hey, thank you so much for joining me on this explainer today.